Hey guys, welcome to new video recording for the physics classes on my YouTube channel. This is continuation of Applications of Biot-Savart Law. In the previous recording, I have discussed the applications of Biot-Savart Law to find the magnetic fields at the center of circular coil and at an axial point of circular coil. Now, the third application of Biot-Savart Law is to find the magnetic field due to a long straight current carrying conductor. Consider a straight conductor XY carrying current I from end X to Y as shown in the figure alongside. Here the magnetic field is to be calculated at point P at perpendicular distance A from point O on the conductor. Since we are going to use Biot-Savart law, we need to suppose a current element at any point on the conductor. So we consider that elemental current or current element of length dl at point A, then join point A and point P. After joining, we have some geometrical values that we need to write. Let me share. Okay, that OP is a fixed distance of the field point from the conductor. R is the radius vector joining the source point and the field point. That is AP is equal to R and OA is equal to L. And angle YAP is equal to theta such that angle OAP is 180 minus theta. The magnetic field at point P, actually the elemental flux density at point P due to the current element of length dl at point A is given by Biot-Savart law as mu naught by 4 pi IDL sin theta upon R square. This is due to this small current element at point A. To find the total magnetic field at point P due to the whole wire, we need to integrate. But before integrating, remember that there are more than one variables. See, as the position of the source point or the elemental length changes, this angle changes, length L changes, and correspondingly R also changes. So there are three variables here. We need to reduce this expression in terms of single variable theta. We do this by considering the right angle triangle in this figure. Check the right angle triangle OAP. From there, remember that you are going to convert that dl and r in terms of theta and a constant. This A is constant because P point is fixed. P point is at a fixed distance from the conductor, so A is constant. So while converting, consider one variable and other constant as a trigonometric ratio. Now, L by A, if you want to convert L in terms of theta and a constant A, L by A is equal to cot, because this is B upon P, base upon perpendicular. So base upon perpendicular is cot theta. Here theta is 180 minus theta in this triangle. And you know, cot 180 minus theta is minus cot theta. So this implies L is equal to minus A cot theta. Now differentiating this equation, you get dl is equal to minus A. The derivative of cot theta is minus cosec square theta. So this gives dl is equal to A cosec square theta d theta. So dl is now converted in terms of constant A and theta variable, only single variable theta. Next, let us convert the variable r in terms of constant A and theta. Again, from the right angle triangle OAP, r upon A is h by p. That h by p is cosec theta. Here, in place of theta, the reference angle is 180 minus theta. So r by A is cosec 180 minus theta, and cosec 180 minus theta is equal to cosec theta. So this implies r is equal to A cosec theta. Again, r variable is also converted in terms of a constant and variable theta. Now, replacing those values in equation 1, we get, just in place. Check that. Mu naught I upon 4 pi, the same here. dl is converted to theta variable and a constant A cosec square theta d theta. Sin theta is same here, and r is converted to A cos theta. So now simplify this and get an expression with a single variable theta, such that you can integrate the equation to get the total magnetic field at point P due to the whole conducting wire xy. Okay. Now remember again that you will get total magnetic field at point P due to this whole wire by integrating equation 2 throughout the length of the wire in angular limits from theta 1 to theta 2. Okay. That means you are going to integrate that equation. Total magnetic field B is equal to theta 1 to theta 2 dV. Put the value of dV from equation 2 and integrate. The constants can be taken out of integration sign. So mu naught I by 4 pi A, all are constants. So they are taken out of integration sign and integrate with respect to theta. This implies B is equal to mu naught I by 4 pi A cos theta 1 minus cos theta 3. You remember that integration of sine, derivative of sine is positive cos, integration of sine theta is negative cos. So after using the limits, you get mu naught upon 4 pi A cos theta 1 minus cos theta 2. Now, as a special case, if the conductor is infinitely long, The angle theta 1 will tend to 0 and theta 2 will tend to 180 degree. Then equation 3 becomes, mu naught by 4 pi a cos 0 minus cos 180. Value of cos 180 is minus 1. So b is equal to mu naught by 4 pi a 1 minus 1. That is, the result is b is equal to mu naught I by 2 pi a. This is for very long conductor, infinitely long conductor. That means if the conductor is infinitely long, and the field point is there, that angle will tend to increase and that angle will tend to decrease. So we use that limitation or limit. Now, if you consider a semi-infinite conductor, semi-infinite means we are going to find the magnetic field at one end of the conductor. That means origin lies at one end and field point is at perpendicular distance from that origin, and the conductor is infinitely long at one side only. This is called semi-infinite conductor. In this case, see, theta 1 is equal to 0, is equal to 90 degree, and as the length of the conductor increases, theta 2 will tend to 180 degree. So the case becomes like that, and if you substitute this value in equation 3, you get b is equal to mu naught I by 4 pi a cos 90 minus cos 180 and is equal to mu naught I by 4 pi a. Remember these results. Again, I want to say the numerical problems can be asked on the basis of general formula for finite length, or the cases expressed in boxed formula, mu naught I by 2 pi a and mu naught I by 4 pi a as special cases. Now let's go to next application of Biot-Savart law, magnetic field due to a solenoid. A solenoid is a helical winding of an insulated copper wire wound on a cylindrical frame, usually of circular cross section, as shown in figure 1. Now we are going to calculate magnetic field inside a long solenoid. Consider a solenoid, very long solenoid of radius a, as shown in figure 2, radius a, and that carries current I in anticlockwise direction at the right end. Those sign represents the direction of current. This cross sign represents the current is into the plane of paper at that point, and those dot signs inside the circle represents current is out of the plane of paper at that point. So at the right end, the current is anticlockwise. Yes, we are going to use Biot-Savart law to find the magnetic field inside the solenoid. Let the field point P lies on the axis of the solenoid. To use Biot-Savart law, we need to consider elemental length. Suppose elemental length dx at point A. Then join A and P such that AP is equal to R. Remember, AP is equal to R, and AM is equal to OX is equal to radius of the solenoid. OM is equal to X, and OP is equal to x naught. That field point P is at a fixed distance x naught from one end of the solenoid. The angle AP, check that figure. The angle APM or APO, you can say, is phi. Now, remember that the elemental length of solenoid is just a circular coil having n turns. That is the circular coil having n turns. So the magnetic field at point P, due to this elemental length, which is a circular coil, that we have already drawn. So we can use the magnetic field at an axial point of circular coil as magnetic field due to this elemental length in this case. That formula is mu naught Ni square upon 2r cube. Yes. In that case, this expression represented the total magnetic field, but here that circular coil is only elemental length of the solenoid. So we write here dB. Okay, in this case also, we convert variables and integrate to get the total magnetic field. Right? Let me share. Here, capital N is the total number of turns in that elemental length. If small n is the number of turns per unit length of the solenoid, then from the definition, it will be number of turns per unit length, and total n will be equal to small n times dx. So the above equation is converted to this one, dB is equal to mu naught n dx Ia square upon 2r cube. Just capital N is replaced by small n dx. Now we will convert the variables using the geometry of the figure. Yeah. Check the right angle triangle MPA. In this triangle, we have cos phi is equal to r by a, h upon p. That means hypotenuse upon perpendicular. This is hypotenuse, and AM is equal to A is perpendicular there. So this implies R is equal to A cos phi. R is equal to A cos phi. Next, you want to convert dx, and dx is x variable is included in side MP of the triangle MPA. So we use ratio, trigonometric ratio MP upon AM, that is B upon P, which is cot phi. Now from the figure, MP is equal to AM cot phi. Yeah, from that trigonometric ratio. From the figure, check MP is equal to MP is this length is total length x naught minus x, and that x naught is fixed or constant. So the derivative of this x naught will be 0. But x is variable, because we can take dx throughout the length of the solenoid. So after the differentiating, we get minus dx is equal to cut phi, derivative of cut phi minus cosec square phi. Derivative of x naught is 0, so minus x gives the minus dx. Yeah, after simplifying, you have dx is equal to a cosec square phi d phi. Now, you can substitute the variables in equation 1 and get the expression as mu naught n I in place of dx. We substitute this value a cosec square phi d phi, and in place of r substitute a cos phi and simplify to get, just simplify this expression to get dv is equal to mu naught n I by 2 sin phi d phi. Now your job is to just integrate this equation, because this flux density is due to that elemental length only. To get the total magnetic field, you have to integrate this equation throughout the length of the conductor in angular limits. That is from phi 1 to phi 2. Okay. Now, yeah, integrate this equation and substitute the value of dv from equation 2. Take the constants out of the integration sign and integrate to get b is equal to mu naught n I by 2 cos phi 1 minus cos phi 2. This integration is just similar to that of the case of straight conductor. Integration of sin phi is minus cos phi, and after substituting the limits, you get mu naught n I by 2 cos phi 1 minus cos phi 2. This is the most general expression. This is true for a solenoid of finite length. Now, as special cases, consider a solenoid of infinitely long solenoid, which is infinitely long. In this case, phi 1 tends to 0 and phi 2 tends to 180 degree. Now substitute these values in equation 3. Yeah, to get this is equal to mu naught n I by 2 cos 0 minus cos 180 degree. Substitute their values and get the result b is equal to mu naught n I. Remember, this mu naught is permeability of free space, means the inner part of the solenoid does not have any solid or any other medium, just air cored solenoid. This mu naught is permeability of free space, n number of turns per unit length of the solenoid, I current, which all are constant. So magnetic field inside a long solenoid is constant. This has many applications. Now, if the solenoid is semi-infinitely long, that means we are calculating magnetic field at one end of the solenoid. Phi 1 is equal to 90 degree and phi 2 tends to 180 degree. After substituting these values in equation 3, we get b is equal to mu naught n I by 2. Check these two expressions. What are these expressions saying? The magnetic field at one end of the solenoid is half of that in the middle of the solenoid. Again, I want to remind you that remember those results for some theoretical problems or numerical problems. Thank you, and this is the end of applications of Biot-Savart Law. If you need any other topics for discussion, you can write in the comment section. I will check and try to solve your problems. Thank you again. Keep on watching.